All right, good afternoon. We're going to start up the webinar here now. Today's webinar is hosted by XD Environmental. We'll be focused on remediation of 1,4-dioxane. My name is Dennis Keene. I'm a Senior Project Manager here at XDD. Presentation will be given by Michael Marley. Mr. Marley is focused on the design and implementation of remedial technologies since subsurface remediation first gained traction in the early 1980s. With over 35 years of experience in environmental and civil engineering, he is a nationally known expert who focuses on strategies for site closure, which includes development and application of innovative remedial technologies for contaminated soils and groundwater. Mr. Marley's presentation will be about 45 minutes long. We'll have a 15-minute question and answer period at the end. If you have any questions during the presentation, please enter them into the questions section of the webinar. We'll compile them and then we'll answer them at the very end of the webinar for that last 15 minutes. So that's the introduction. We'll now hand the webinar over to Mr. Marley, and thank you very much.
Okay, thank you. First of all, thank you everybody for attending the webinar. As Dennis mentioned, this is going to be focused on remediation techniques for 1,4-dioxane. It's based on both our own experience in working with 1,4-dioxane, but also a number of colleagues in the industry who have been either researching or working from the application perspective in the industry, have also provided a number of slides that are included in this 38 slide presentation. The agenda, basically we'll talk a little about the properties of dioxane with respect to remediation, and then we'll get into the discussion of the remedial technologies themselves with a number of case studies. We're first going to touch on some of the more reliable or proven technologies, and those tend to be the ex-situ, advanced oxidation, some absorption, and some in-situ applications. And then we'll discuss some of what I'm terming as promising remedial in-situ technologies. Doesn't make them any less applicable, but they're just not as many applications that have been done in the real world as yet. This slide basically always of interest and always questions about it. There's a couple of different things about it. The pie chart on the right is what I'm really focusing on, and this came from a CERTA presentation. I took this and recognized Pat Evans of CDM Smith for providing this slide. There's always a question about 1,4-dioxane and its presence associated with TCA or TCE or whatever different chlorinated solvent. When you read the literature and you look and do some research on it, there's a lot of suggestions that it was present as a stabilizer in the production of the TCA, and the various percentages that it was quoted. I've seen anywhere from 2% up to about 10%. But I also seen references that it was also up to a smaller percent in TCE. And there seems to be some debate about whether that is correct or whether there is basically the TCE has had TCA previously that has degraded and left with TCE. So there is a little bit of debate about that. But as I said, there is references to suggest it was also used as a stabilizer. There's also suggestions in the literature that, again, when you see it in situ, you can have concentrations that exceed what it was included in the actual production or production of the chlorinated solvents themselves, in the degreasers that were used in the facilities that use these chlorinated solvents, there would be concentrations of the 1,4-dioxane, therefore getting higher percentages that may have been released into the subsurface. With respect to the properties of 1,4-dioxane remediation, this table sort of shows it in comparison to some of the other contaminants that we would deal with normally in situ. We've got solubility, and you can see that 1,4-dioxane is miscible. Essentially, it's got an infinite solubility in water. Some of our MTBs got a high solubility, whereas the PC and benzene get more reasonable solubilities. The KOC is an indicator of its ability to be absorbed on organic carbon materials. And again, you can see that 1,4-dioxane has got a reasonable absorptive capacity, but it's nowhere near what it is for the like of benzene and for PCE, and it is slightly better than it is for MTBE. Henry's law coefficient is an indicator of how it may partition from the aqueous phase into the vapor phase, important for things that like looking at strippers above ground. And you can see that the 1,4-dioxane has a very low Henry's law coefficient. Similarly, MTBE has a low one, but an order of magnitude or two higher than for 1,4-dioxane. But both are significantly lower than it is like for what we know to be strippable compounds such as PCE and benzene. What this means in ex situ treatment is basically for the residence time that is typical for an air stripper, it's unlikely that MTBE or 1,4-dioxane would be effectively stripped cost effectively above ground. However, as you'll see in the discussions that we have in the in-situ technologies, the residence time is much greater for these compounds in a site situation, and therefore there is capability to have some degree of stripping, which we'll talk about in a little later. Vapor pressure is an indicator of the pure compound's volatility and its ability to be stripped with the like of soil vapor extraction. You can see here that 1,4-dioxane is very reasonable of the same sort of volatility as a PCE. MTBE in this particular case is very high volatility as a pure compound, and therefore if it's existing as a residual, it could be readily stripped by soil vapor extraction. Again, you'll see an example of this for 1,4-dioxane presented later. Water quality criteria for dioxane, this is a bit of a moving target on a state-by-state level. As we know, there's no federal MCL as yet, but the states all seem to be getting down to the low ppb or sub-ppb level. An example, New Jersey just went to an interim groundwater quality criteria of 0.4 ppb for 1,4-dioxane. So what do these properties mean? It's volatile as a residual product. Unfortunately, we don't see it in that form much. Very soluble in groundwater, will therefore not easily absorb, will therefore move readily in the subsurface, and typically can be seen on the leading edge of a plume. We'll get right into the ex situ technologies. Again, I've chosen these first because there's more examples where they've been used and the technologies have been more proven. The two technologies that I'm going to talk about with regard to ex situ is advanced oxidation, and the key is the formation of the radical chemistry associated with advanced oxidation processes. And then we're going to talk about sorption. I mentioned earlier that based on the properties, one would not expect 1,4-dioxane to be highly absorbed on organic matter, and that is correct. But on synthetic materials, you can have significant effectiveness with regard to the absorption of the 1,4-dioxane. Let's talk first about the advanced oxidation processes. This is actually a case study that we're working on, and it is probably a very typical situation that one of the typical situations you're going to come across with regard to a 1,4-dioxane problem. This was a long-term pump and treat system that's been operating at a facility for a number of years, and again, it wasn't until more recently that 1,4-dioxane was of interest and it was requested to be analyzed for. In this particular case, and in many of the cases where there's chlorinated solvents involved in the treatment system, 1,4-dioxane, when it was analyzed for, was found in the influent to the groundwater treatment system. And in this particular case, it was around about a few hundred ppb, which has declined over time, but is still above the criteria. And the groundwater is currently being treated by what was popular back in the day, which was the powdered activated carbon sand filtration type systems. And as one would expect, the absorption of the 1,4-dioxane, which wasn't accounted for in the design because it wasn't a concern at the time, is not highly effective, and therefore the 1,4-dioxane was passing through the system fairly untreated. So the approach to this is to modify the system to add a module that has advanced oxidation capabilities to treat the 1,4-dioxane at the end of pipe before discharge. A complication of this particular site, which is not at all sites, is the presence of bromide in the groundwater in exceedance of the or significant concentrations. As you're aware, oxidation of bromide can form bromate, and bromate has an MCl of about 10 ppb. So it brought a complication here, as we will discuss in this advanced oxidation case study. The actual advanced oxidation process, which is a typical in-situ process, is the use of hydrogen peroxide and ozone. When combined together, they react to form hydroxyl free radical, which is very effective in destroying a lot of contaminants, including 1,4-dioxane, very rapidly. Unfortunately, the presence of the ozone can also cause the formation of the bromate. And so there's a balancing act here where the molar ratio of the hydrogen peroxide to ozone needs to be balanced so as to destroy the 1,4-dioxane, at the same time not creating a significant bromate concern. So this is the balancing act. If we add more hydrogen peroxide to the ozone, increase that molar ratio, we're taking care of a lot of the ozone, and the benefit of that is it's not available to react with the bromide, and therefore would minimize the formation of bromate. However, the hydrogen peroxide is also a scavenger for the hydroxyl radicals, and therefore you can affect the effectiveness of the reaction on the target contaminant, in this case 1,4-dioxane. So it's a sort of trade-off or balancing that you need to do to make sure that you accomplish both goals. There is other ways to form the hydroxyl radical. UV is one, but it also has its issues with regard to operation and cost. This is some data from a treatability study looking at a singular molar ratio of 1:1 for the peroxide to the ozone, and looking upon its effect on the treatment of the 1,4-dioxane and the formation of the bromate as a function of increasing the concentration of the oxidants while maintaining the molar ratio of the 1:1. And so on the left columns, the impact on the 1,4-dioxane, you can see as we increase the concentration of the oxidants at the fixed molar ratio, we get good destruction of the 1,4-dioxane down to the 1 ppb level or less. However, with that same molar ratio, you can see as we increase the ozone concentration, maintaining the molar ratio, we are starting to form significant concentrations of bromate in excess of the MCl. Therefore, this particular molar ratio of 1:1 in this particular groundwater with the presence of the bromide has potential issues of treatment effectiveness. This now looks at increasing the, this next slide looks at increasing the molar ratio of peroxide to ozone. And basically looking at a molar ratio of, previously it was 1, we've increased the molar ratio to 2.5 and 4 of peroxide over ozone. As I mentioned earlier, the benefit of that is the ozone's quickly taken up in the reaction, and they're less available for formation of the bromate. However, the additional hydrogen peroxide can react with hydroxyl radicals formed and scavenge them, potentially affecting the effectiveness of the treatment of the 1,4-dioxane, and that's exactly what we see in this particular case, where you see for the 2.5 molar ratio and the 4 molar ratio, as you increase those ratios, you start to see a less effective treatment of the 1,4-dioxane, and you see concentrations now that exceed the target concentration that was 3 and dropped down to 0.4. However, as expected, again, based on the chemistry, as you increase that molar ratio of hydrogen peroxide and you scavenge or react the ozone, you start to see a drop in the concentrations of bromate. So to below the MCL. So the whole point of this is oxidation processes for 1,4-dioxane are very effective. It can be complicated when you have to deal with bromide in concentrations in exceedance of your MCL of 10 ppb. Sorption, as I mentioned before, granular activated carbon effectiveness on 1,4-dioxane for above ground requires a significant residence time and significant quantities of granular activated carbon, and therefore there's a question about its cost effectiveness. Dow developed a number of resins that have the capacity to have significant absorptive capacity for 1,4-dioxane and other contaminants that are not as readily absorbed on activated carbon. The next few slides were provided by Steve Woodard of ECT Squared that basically deals in this, the availability of this adsorbent material. And Steve provided a case study for a site in Florida that operates at about 140 gallons per minute. It's had dioxane concentrations as high as almost 3 parts per million. More typically, the concentrations seem to be in the hundreds of ppb, similar to the landfill site. Total organics about 18 ppm, and iron concentrations to deal with as well. And this is the results from the adsorbent material that is used at this particular site. As you can see, the concentration in the influent is bouncing around the 50 to a couple of hundred ppb level. The permit is at 3 ppb, and the concentrations that are being achieved are significantly less than the 1 ppb level. So showing the effectiveness of this particular absorbent on the treatment of 1,4-dioxane. Shifting to in-situ technologies, we're going to talk again about in-situ chemical oxidation. We showed through the ex-situ treatment processes that the can be very effective once you form the radicals. It's not only the hydroxyl radicals that have the energy necessary to do the destruction. Some of the other radicals like the sulfate radical can also have that capability. So this is a case study, another case study of our own, where a industrial facility in the Northeast had a typical suite of chlorinated solvents and 1,4-dioxane at concentrations in the tens of ppm. Dioxane was about 3 ppm in this. It was silty sands. It was a fairly small source area directly under an operating facility that was doing 3 8-hour shifts. So peroxide, which could have also been used and was effective, or can be effective through the formation of hydroxyl radical, was eliminated from consideration because we were directly underneath the operating facility, and there was concerns with the gas formation and the potential to move vapors into the building where people were operating the facility. The treatment goal here was only to knock it down. It was a typical combined technology remediation case study where the source was not to be treated to MCL levels. It was to be knocked down so that natural attenuation would reduce the contaminant concentrations such that at the property boundary or receptor there would be acceptable concentrations in the groundwater. A treatability study was performed, or we performed a treatability study and determined that the appropriate technology would be alkaline activated persulfate. It was going to be safer to use than the peroxide chemistry or the ozone chemistry at the particular time. It had greater stability in the subsurface to allow for migration to the contaminant and contact time, and obviously reduced potential for gas evolution. To do alkaline activated persulfate, you need to make sure you account for the soil buffering capacity, so you need to do a test to find out what that buffering capacity is. And you also need to add enough buffer so that the acid that's formed through the dissociation of the persulfate is also taken care with, or the pH will drop below the target 10.5 pH level for alkaline activated persulfate, and you'll be dealing with an unactivated persulfate system in that case, which will not be as effective in some of these contaminants. So we had to add about 15,000 kilograms of sodium hydroxide to both overcome the buffering capacity of the source area, but also overcome the acid production from the sodium persulfate, the closure that was used, 31,000 kilograms. That was injected over 2 injection events, and you can see that basically the target contaminants, TCA, PCE, and 1,4-dioxane were reduced significantly below the target level of 1 ppm into the tens of ppb levels that was attained. An interesting fact, again, you may be aware, 1,1-TCA is a highly oxidized compound. It's not readily oxidized. It actually has to be reduced first, and both alkaline activated persulfate and peroxide systems can produce the superoxide radical, which actually is a reductant and can initiate that process of the treatment of 1,1-TCA, which was done in this case. Alkaline activated persulfate creates a very complex soup of radicals, including the same sort of radicals you get from hydrogen peroxide with the hydroxide radical, the superoxide, the peroxide, different radical species as well as the sulfate radical. There is other in-situ chemical oxidation processes that can work for 1,4-dioxane. A recent, and you'll see in some of the case studies that I provide here that are lab treatability studies, a lot of those are funded by the Department of Defense, either through their CERTIP program or their ESTCP program. The difference there is the CERTIP is basic research normally done in the lab, and the ESTCP usually takes it into the field to do a demonstration. In this particular case, I haven't given any slides on this particular one, but you can find it in the literature. Keras, in coordination with a couple of universities, done a study where they looked at these cylinders that were combined persulfate and permanganate that slowly release those chemical oxidants into the environment around the cylinder, and they were shown to be effective in the treatment of the 1,4-dioxane. Again, what I interpreted from the data was it was, again, an activated persulfate that basically was the primary destruction mechanism for that particular study. But again, you can read and form your own conclusions. That paper is readily available in the literature. Obviously, anything else that produces hydroxyl radical, other peroxide systems, ozone systems, Fenton-type systems, will also be effective for treatment of the 1,4-dioxane. As again, with the in-situ, it's a matter of getting that contact to be effective in the treatment. We move on to some of the more promising remedial technologies. I've listed 4 here that I was able to find information or get information on or read on ourselves. And basically, I underlined the 3 that I'm going to talk a little more about in the subsequent slides. They are stripping, the thermally enhanced SVE, and bioremediation. I also mentioned phytoremediation. I found one case study. There may be more, but it was, again, the use of poplar trees in a shallow plume with 1,4-dioxane. And the monitoring demonstrated the control and removal of the 1,4-dioxane from the shallow groundwater. And the analysis that was done as part of that study indicated that the primary mechanism wasn't the destruction mechanism of the 1,4-dioxane in situ that sometimes happens at the roots associated with the phytoremediation, but actually was absorbed into the system through the water, then transpired from the trees out into the atmosphere where they're expected through photocatalysts to basically degrade rapidly. So let's get into the other promising technologies, and we'll show you some case studies associated with these technologies. Air stripping. I need to spend a little time on this because, as I mentioned earlier, the Henry's coefficient associated with 1,4-dioxane is extremely low. So it is certainly perceived that it is not something that would be effectively strippable. However, when thinking about this, most people are thinking about air strippers and above ground ex situ, similar to the thing for MTBE. But there is a number of case studies out there showing MTBE being stripped in the subsurface through our sparging systems. And one of the things that we did internally is we have a model to predict the strippability of contaminants, and we looked at 1,4-dioxane. And while we found that a singular curtain of our sparging wells would have difficulty stripping off the 1,4-dioxane under normal groundwater flow conditions, a multiple barrier system may be effective or could be effective for doing that, based on the fact that there is a partitioning to the vapor phase. It's just at a low rate. So I got these slides. I looked in the literature, and I got these slides from Mohammed, who basically works for ART, and you'll see some of these slides. And this is a site that they've done a demonstration on with 1,4-dioxane, and were successful in reducing the concentrations of the 1,4-dioxane in the aquifer. This basically sort of shows what I discussed a few minutes ago, which is the ART system basically is an in-well stripping system. Groundwater is drawn into the bottom of a two-well system and two-screen system, and the water in the well is stripped. There's a sparging in the well itself, and then the water exits the well at the top screen, creating a recirculation within the aquifer if the hydrogeologic properties are conducive to that. And as expected, the residence time in this individual well would typically not be sufficient to strip the 1,4-dioxane. It would be similar to like an above-ground air stripper, in that that residence time may not be sufficient. However, in situ, where you are recirculating that water several times through the same device or through the same well, at each stage you would expect an additional amount of stripping to occur. And according to this analysis, 9 stripping passes would result in a significant % removal, similar to what the theory and the model that I described earlier that we had ran had shown, that a singular sparging well at the typical groundwater flow rates would not be sufficient, but multiple passes or multiple curtains lined up would be effective in reducing the concentrations. So this is the case study, which was bedrock overlaid by saprolite soils. Levels had gone to an asymptotic condition, and a demonstration was done of the in-well stripping system. And these are the results from that demonstration, where initial concentrations in the monitoring wells are up in the ppm levels of 1,4-dioxane, and they had dropped over about a 90-day period, about between 80 and 90%. In discussing the results with Mohammed, basically just to prove that the 1,4-dioxane was actually being stripped, there was measurements of the vapor concentrations that were emanating from the well, and 1,4-dioxane was measured in those in the extracted vapors, and there was about 2¼ pounds removed during that demonstration. In discussing it a little further, the mass balance on the amount that was removed by the reduction in the concentrations was not equal to the number of pounds removed as determined by the vapor phase, and therefore it is speculated that there is some biodegradation that's going on under the aerobic conditions that are created in the environment, and obviously there is partial stripping. And we'll talk a little more about the bioremediation aspects when we get to that stage of the discussion. But that shows that, again, 1,4-dioxane is not something you want to jump out and try to strip under normal conditions, but under field-specific conditions where you have the residence time, or you have that ability to do multiple stripping either through an ART system or through multiple curtains, there is a potential to drop those concentrations down significantly. Thermally enhanced SVE. I'd mentioned that as a residual product, the volatility of 1,4-dioxane is actually very good, and would expect it to be readily strippable. Unfortunately, most of the time it actually is in an aqueous phase, and therefore basically the Henry's coefficient is low and therefore affecting its partitioning into the vapor phase for stripping. These slides were provided by Rob Henchy of Integrated Science and Technology. Rob's down in Florida, and basically they done again a demonstration under a ESTCP, which again is a DoD funded program in conjunction with Arizona State University and Colorado School of Mines, NACOM. And the results of that, Rob was good enough to share with me and be able to present today. First of all, theoretically, again, 1,4-dioxane, like any contaminant, typically the Henry's coefficient is a function of temperature. As you increase the temperature, there's a bigger tendency for it to move into the vapor phase as opposed to stay in the water phase. So by heating up, you're going to improve that Henry's coefficient significantly, which can affect the ability to volatilize it and be extracted by vapor extraction. Also, if you heat up and you remove moisture from the system, that will also help again in removing the 1,4-dioxane. So the process here was to increase the temperature within this VATO zone. Obviously, we're dealing with soil vapor extraction, where 1,4-dioxane was present. This demonstration was performed at the former McClellan Air Force Base in California. As you can see from the cross-section, we're dealing with salty sand, sandy silt material. And the target interval, again, above the water table, affected by the 1,4-dioxane. The design basically is about 20 foot on center well, injection wells that are used to inject heated air into the subsurface, the unsaturated zone. And you can see at about 100 CFM was injected into the subsurface within the target interval, which was about 40 to 70 feet below ground surface. There was a central extraction well which was operated at 100 CFM. And basically the system was just used to warm or heat up the subsurface temperature to enhance the volatility and the removal of the 1,4-dioxane, and using the existing vapor treatment and collection system, condensation system. This is some of the data. If you look at the vapor concentrations, you can see the concentrations were pretty low to begin with, but as the subsurface heated, you were able to increase that vapor concentration significantly, and you can see the typical track of vapor versus time with an SVE system, where you get an initial higher spike and then it declines in a sort of exponential manner with time as you start to remove the contamination that is present in the subsurface. You can see that the removal of about 13 kilograms were removed over the year of treatment period. The objectives were to reduce the dioxane by about 90% in the unsaturated zone, treatment zone, and as with all thermal systems, there's always a concern about mobilization and downward migration, so that was being monitored too at this particular site. As you can see from the results, the system worked. The 1,4-dioxane was removed greater than 90% in the treatment area, not only based on the estimated mass that was there and the mass that was removed, but also by soil samples that were taken before and after the demonstration. And the data did not show any apparent downward migration of the 1,4-dioxane. So again, where you have a situation where you have a VATO zone with 1,4-dioxane, I think also, I didn't provide all the slides that Rob gave me, but he was also thinking that even traditional SVE without the heat may have some capability of doing this removal as well, similar to the stripping that we see with the ARC system and our own analysis based on the Henry's law coefficient. Getting towards the end of the slides, we get into talk about, I think, one of the more interesting, or the most interesting of the remedial technologies that may be available to us as well as bioremediation. Research in the literature basically demonstrates that there has been, for actually quite a number of years, there has been work that's been done looking at the 1,4-dioxane and its biodegradability. I think as far back as the early 90s, there was some work done identifying organisms that could use 1,4-dioxane as their energy source. The noteworthy one that appears in most of the literature is this CB1190. The trouble is that it seems to be that these organisms that are capable of degrading 1,4-dioxane as an energy source appears to be not as common and available as some of the other ones that we'll talk about later in this slide. And it appears to be more difficult maybe to grow these in a in-situ environment, such that they may be more difficult to follow that sort of line of reasoning to go after an in-situ bioremediation project with the direct energy source type of microorganisms. Not that it can't be done, but it may be a lot more difficult than some of the other options that we have available to us. What also you see basically is a lot of work's been done looking at co-metabolic processes. And for those that are not as familiar with that, that means that there is another substrate which is basically the primary energy source that the bacteria basically will degrade to obtain that energy. And in that process, the enzymes are capable of basically degrading also the 1,4-dioxane. So it's not the primary food source, but it is, as a consequence of the degradation of the primary food source, is able to degrade the 1,4-dioxane. And THF propane in particular we'll talk about with the case study, toluene, and there's others that have been determined to be effective energy sources for the bacteria and having the complementary process of destructing or degrading the 1,4-dioxane. A commonality that was observed in all this research work was done with these monooxygenated enzymes that are available in these systems and seem to be a significant part or importance with regard to the 1,4-dioxane destruction. Under anaerobic conditions, there's a couple of cases that we'll mention. This particular one, again, a DoD-funded project back in 2007 by Rob Steffen and his group. Rob was with Envirogen, as I was back in the early 90s. And Rob done this study with his group again in looking at whether 1,4-dioxane could be destroyed under anaerobic conditions. Rob, Envirogen was acquired by CB&I, and that's why he's got that label after his name now. What they determined from that study was they didn't see any significant destruction of the 1,4-dioxane under any of those anaerobic nitrate, reducing iron, reducing sulfate, or methanogenic conditions. They were not able to determine much in the way of anaerobic degradation. As with many of this, I won't be surprised in years to come that somebody determines that there is a way to do it anaerobically, but current knowledge sort of says that is not the best track to follow. So we get into the co-metabolic, which we know has been is more of a proven method to do the destruction of the 1,4-dioxane. These slides are provided courtesy of David Lippincott of CB&I, formerly again Envirogen, that basically has done a demonstration study again for the Air Force Civil Engineer Center, looking at this in situ and sort of saying, can propanothropes, which are more common around all the environments, the subsurface environments, they're fairly common. The issue is whether you can grow them up to sufficient numbers effectively and in a reasonable time frame to basically do the destruction, or whether bioaugmentation would be a better for your particular site case study. So this was some lab work that was done by Dave and his group for a site at Vandenberg Air Force Base, again funded by the Air Force. And what you see in this is, what was interesting about this that's not on the slide is, they actually, in looking at the shallow zone actually had quite a population of propanothropes, and therefore basically had the bacteria present to do the destruction. But the deeper zone at this particular site didn't have a good population of propanothropes. And so that was the one that was focused on with regard to the demonstration. not only for the degradation of the 1,4-dioxane, but also to basically see whether you could enrich the propanotropes that were there in low number, or whether bioaugmentation would be needed. And the strain that was used in this particular demonstration is ENV for Envirgin, I believe, 425. And basically the goals here was to see whether it would work in situ and also to achieve a low 1 ppb level within the deep zone. What this diagram or microcosm diagram shows is there was a number of conditions that were evaluated using oxygen only, which again we wouldn't necessarily expect to work by itself. Using oxygen with the propane, which again is the primary energy source utilized for the bugs. Using the oxygen, propane, and nutrients, and this particular gaseous nutrient to basically introduce it to the subsurface, and at the same time as propane. Kill control, as this is a lab treatable study. The bioaugmentation with the adding the propanotropes at a density sufficient to demonstrate degradation. Anaerobic was also looked at, and then looked at, there's a question mark out there whether methanotropes can also degrade the 1,4-dioxane. So this was looked at in the presence of, again, nutrients, diammonium phosphate. And what you can see from here for this study, which was over a couple hundred days, was that the only condition upon which you could see significant degradation was under the bioaugmentation case. Now, they also did see that propane enrichment culture eventually would grow on this, but again, it was a longer period of time to grow that population naturally. But under bioaugmentation, there was significant, especially when the nutrients were added to the system, there was significant degradation of the 1,4-dioxane, including respiking of the system, to take a look at that. So the microcosm results showed for the deep zone, again, it would be beneficial to add bacteria if you needed to get degradation in a reasonable time frame. So a demonstration was performed at Vandenberg in a controlled area that basically start up at about 10 CFM, and we've done 1 month of sparginoid to oxygenate the system. Then they basically added the propane in at about 40% of the LAL, and doing different cycles. It was a cycled sparging system, which is always better for distribution in my mind. In day 42, they added the propanotropes, the NV 425, and nutrients, and then basically monitored the system. And this is the results of the system. And as you can see, if you just look at the table, certainly you can look at the figures, but in the wells that were within the area of influence of the distribution of the propane and the oxygen, which didn't include 5A, which is actually in the intermediate aquifer above the deep aquifer, and 5B, which also had some hydraulic connection issues with the rest of the aquifer, they got a high % reduction in the 1,4-dioxane as a result of this demonstration. You can see here, this was written up in the Groundwater Monitoring and Remediation article published in 2015, and again is available to you to get a more complete story on that particular study. I also wanted to present this. This is another CERTIP funded by Dave Adamson and group out of GSI, and it's also published in 2015 under ES&T, and it was an interesting article. And what it was is basically they went to the California GeoTracker data source, and they also got information from a number of Air Force sites or wells, and they looked at that information with regard to what was happening with the 1,4-dioxane as a function of time on these sites where there was no sort of active remediation ongoing. And what they found from this is on the California GeoTracker, about 30% of the 193 California sites had a statistically significant source decay term. About 23 sites had about an order of magnitude reduction, and very few had greater than that. So order of magnitude reduction was achievable, but getting to 2 or 3 orders of magnitude reduction under natural conditions was not frequently observed. Similarly, for the 441 Air Force wells that were monitored, about 30% of them had decreasing trends, whereas the rest basically had either stable or in a few of the cases, 9% with some increasing trends. What was interesting was that the Air Force wells, when they looked at what the attenuation, where you did get significant declines, what did it correlate with? And there was a positive correlation with dissolved oxygen, which basically ties back into the discussion on the bioremediation, where if you have an aerobic system and you have the presence of other potential energy sources, such as the propane or other potential contaminants, you have that potential for co-metabolic degradation of the 1,4-dioxane. And there was a positive correlation between the presence of oxygen and the degradation that was statistically significant. There was negative correlation where you had the presence of other chlorinated solvents or metals. If you read in the literature, you'll see that there is a number of discussions where the presence of other chlorinated solvents, especially at high levels, may be having an inhibitory effect on the degradation of the 1,4-dioxane. In the study that I just presented at Vandenberg, they did have other chlorinated solvents there, but they were at fairly low concentrations, and the thought is that basically they weren't high enough to maybe affect the ability or inhibit the degradation of the 1,4-dioxane. The other thing that came out of this was the median half-life, where there was statistically significant attenuation, was about a 2 to 4 year half-life. So slow degradation under natural conditions, and again, only in about 30% of the cases. The last thing, last slide, basically provided was there has been a lot more use. We've done it ourselves at a number of sites where we need to have more definitive information on the degradation. And both PACE Analytical and Microbial Insights do provide stable isotope or qPCR methods to basically demonstrate fairly definitively that the 1,4-dioxane would be being degraded, both in the the removal of the 1,4-dioxane, but also the appearance of the heavier carbon isotope in either the biomass or the byproducts of the degradation process. So I thank you for your time, and Dennis, if there's any questions that basically have come up, we can certainly try to address as many as we can. Sure,
we have 2 questions. The first one is with respect to lower level influent concentrations for likely pump and treat systems. The question is there a treatment technology more suitable to remediating lower concentrations of 1,4-dioxane, for example, influent dioxane at 100 ppb?
The advanced oxidation processes have no problem even at the concentration. Probably the absorbent technologies also are able to do that low concentration influent. The question that I'm typically asked, I'm not sure if this is what the intended point was, but I've been asked several times about home systems. Basically, is there anything that's cost effective to put in a home? And unfortunately, the short answer is no. The absorbent technology is none of these technologies are low cost technologies for pump and treat systems. Obviously, the in-situ technologies can be cost effective depending on the site-specific conditions, but there's no technology that I'm currently aware of that basically is very low cost. Obviously, we talked about bioremediation. There has been demonstrations of bioreactor systems. So when you're talking about treatment on a pump and treat system at a site, you do have the absorbent technologies, you do have the advanced oxidation technologies, and you do have bioreactor technologies. Some of these, again, you'd be safe. You should be doing a demonstration because there's not enough. They're not far enough along, basically, in all cases, that there's a high degree of certainty in it happening for your project without a demonstration. But I think those are the 3 primary technologies that I'm aware of that would be considered for a pump and treat.
Just as a follow-up, someone asked whether or not there were actually any successful applications for remediation at a point of use, type of situation for private wells. Whether or not it's expensive or not, are there systems out there that you can install for a point of use on a private system?
The other technology that we didn't discuss for like a point of use for like a home system was reverse osmosis. There's been some work done with reverse osmosis, and I think the demonstration was around 80% reduction in the concentration of 1,4-dioxane with the reverse osmosis system. We can certainly forward that question, or feel free to contact Steve Woodard. Can certainly give you, if he's had any case studies where he's used his adsorptive technology at the point of use system. I'm sure there's some on the bioreactors. I'm sure there's some additional work that could be seen, but I didn't come across anything specific other than the reverse osmosis example.
Next question is a little bit broad, but maybe we can narrow it down a little bit with respect to some of the key parameters for site-specific that you need to understand for the remediation of 1,4-dioxane. The question is, could you please explain a little bit about how to select the suitable remediation technology for 1,4-dioxane based upon the site-specific conditions? So it's a bit broad.
It is very broad. It generally comes down to a cost-benefit analysis, and for example, it is a very wide sweeping. But if you're dealing with clay materials, as an example, you're not going to expect something like most of the in-situ technologies are going to have difficulty in clays because of the ability to distribute whatever amendment, whether it's biological or chemical or air, if you're doing it, it's considered an SVE. So there's some things like that that are pretty sort of obvious. But for a typical site where you've got, say, silty sands or heterogeneities, you're looking at a cost benefit. The different technologies all have potential application. If you've got something that's a very widespread plume that basically associated with the 1,4-dioxane, doing something like chemical oxidation is going to be very costly because the amount of mass that you have that for the 1,4-dioxane to destroy is very minor, and the chemical demand that is non-target that the soils require to treat them to get to the 1,4-dioxane could be substantial. So it depends. If you've got a widespread plume, maybe your pump and treat containment, maybe your biological system where you're introducing air and propane over a large area may be more cost effective, whereas your chemical oxidation may be more applicable for a hotter source area where you're dealing with the 1,4-dioxane and other contaminants that are also situated at that. So I think what we do is typically in a situation like that where someone will come and basically say, here's my problem, what's my answer? We'd basically do a matrix of options, and we'd look at the cost, we'd look at the technologies, and we'd look at the site-specific conditions, and we'd determine which ones would be more applicable, what's the certainty of success with the technology, what's the cost of the technology, what's the issues.
A couple of questions with respect to the bromate. First question is, where's the bromate coming from? And the sort of addition to that is, with respect to any sort of information that we have with respect to regulatory bodies reacting negatively to bromate formation in lieu of 1,4-dioxane reductions. So kind of two parts there.
Yeah, and I think bromide concentrations tend to be higher where you've got like if you've got a landfill, for example, that kind of God knows what went into it basically, or you're near salt water or more brackish water that might have it. Those are situations where you'd want to look at the bromide and expect to maybe have higher concentrations to deal with. With respect to the regulatory, again, I think there's quite a few regulators on the seminar, or webinar, so they may be able to answer that question better than I. My experience is obviously it's different state to state how they might consider that. Is there a net benefit to not worrying about the bromate? Is it even of a concern to them at that particular location. That's a difficult one to answer because I think the answer is going to be a lot different depending on what state you're dealing with and the site-specific circumstances. But I could see where there would be cases where the formation of bromate at low levels, maybe above MCLs, but in a limited area, basically might be more acceptable than the 1,4-dioxane.
So another question was, we have 4 minutes left here, so probably another 2 or 3 questions at the most. The question was high temperature remediation, incineration as an example. Is that a viable option? Any particular end products associated with that or byproducts that need to be worried about that? So you take soil or something like that for incineration.
Good question. In incineration, the first thing that comes to mind is it's costly. It can be very costly. Is there something that we can do better? And most of these technologies that we're talking about here are going to be more cost effective than excavation and incineration of the soil. I honestly don't know off the top of my head whether 1,4-dioxane is going to form a byproduct of major concern. I don't see it, but basically I don't have a definitive answer for whether there would be a byproduct. I would be more concerned with what else is in the soil that could form something of concern than the 1,4-dioxane itself. But again, it would be low on my list, to be honest with you, if I had an in-situ situation that could be treated by some of the other technologies, because I know it's going to be more cost-effective. Again, if you're dealing with a clay and there is a risk associated with it that can't be managed, that might be something to consider.
Okay. Maybe just 1 or 2 more here. So the question was, with respect to, not with respect to bromate, but are there any other byproducts from the 1,4-dioxane advanced oxidation processes?
Yes, it's an interesting question because all chemical oxidation or all oxidation processes, or certainly chemical oxidation processes, if you look at the stoichiometry between how much oxidant it would take to mineralize the contaminant and how much is used or necessary to destroy the contaminant in the field, you find that the amounts that are used in the field are typically much less than the stoichiometry requirement to mineralize it. So it is typical for byproducts to be formed as a result of chemical oxidation. Typically, it depends on the chemical, obviously, as to what that pathway is and what that byproduct might be. But typically, the byproducts are themselves oxidizable or break down into a much more readily degradable contaminant or are of less concern from a regulatory perspective. So the formation of byproducts as a result of chemical oxidation, in fact, it happens. Under most cases, what forms is also oxidizable with more residence time, or it is more readily destructed by other mechanisms such as biological processes. So yes, be aware that there is likely byproducts, but typically they're not of major concern.
Okay, we got 1 more question here. For the co-metabolic case study, was oxygen injected during that study?
Well, it was air sparging that was performed in that particular site. So oxygen was introduced as part of the air, and you do need the oxygen present, obviously, to it's an aerobic bacteria. You need the oxygen. You can use air. Or oxygen can be injected to provide the air. Once the aquifer was oxygenated enough, they started to introduce the propane to the process as the primary energy source, and then basically in that particular case it was bio-augmented in the deeper zone because the population of protanotrophs were low, and to get the job done in a reasonable time frame needed the bio-augmentation.
Okay, and then there's several questions, not related to presentation itself, but we're going to be wrapping up. We will be making the slides available for the attendees of the webinar, so look for that email. We'll do that probably this afternoon as far as setting it up. And I think that's it with respect to questions. We appreciate everyone attending. And if
Thank you for your time.
Have any additional questions afterwards that come to you, or you didn't have a chance to ask them, you can email us at info@xdd, and we'll make sure to answer them for you in any way.
Right, or my email address is on that last slide too. Feel free to contact me. I'm I don't bite.
Generally.
Generally.
So thank you very much, and we're going to end the webinar right now. And again, we appreciate it very much. Thank you.